Hello, my name is Vadim Greenberg, and today I'm going to present you our joint work with Putima Gamlath, approximating star cover problems. We will start with several definitions. Consider a finite metric space F union C with a distance function d. We'll call elements of F facilities and elements of C clients. A star is a tuple ICI, where I is a facility and CI is a subset of clients. A star cover is a collection of disjoint stars that cover the whole set C of clients. The load of star ICI is the sum of distances from star center I to all clients in CI. And finally, the load of a star cover is simply the maximum load of stars forming it. In our work, we studied two problems on star covers. The first one is minimum load K star cover. Given an integer k, find star cover of size at most k with minimum load. The minimum size star cover problem is basically the reflection of minimum load k star cover. Given a non-negative number t, find the star cover of load at most t with minimum size. These problems seem to be one of the most poorly studied ones in the field of facility allocation problems. As shown by Even et al., both problems are NP-hard for general metrics, even when sets of facilities and clients are the same. For the latter case, however, several constant factor bicriterion approximation algorithms have been developed. Recently, Ahmadian et al. Has shown that minimum load K star cover remains NP-hard even for line metrics, and provided a p-task for this case. However, we don't know any previous algorithmic results that cover bicriterion approximations for general case, when sets F and C are not the same. This case will be our main focus. We obtained first constant factor bicriterion approximation algorithms for the general case of minimum load K star cover and minimum size star cover problems. Precisely, given arbitrary positive constant epsilon, for minimum load K star cover, we find a star cover of size at most 1 plus big O of epsilon times K, and load at most big O of 1 over epsilon squared times the optimum. For minimum size star cover problem, we find a star cover of load at most 2 plus epsilon times T, and size at most big O of 1 over epsilon squared times the optimum. Quite a similar bound. Both algorithms work in polynomial time for any metric D and any set of facilities and clients. In the remaining part of the talk, I will describe our algorithm for minimum load K star cover problem. The algorithm for the other problem uses the same ideas and can be obtained just by rearranging some steps and carefully choosing parameters. Our approach is based on linear programming. First, we define the polytope as CTK. Its integral feasible points are exactly star covers of load at most T and size at most K. Here is the LP description of the polytope. We have opening variables yi for facilities and assignment variables xij for every facility client pair. The first constraint of the LP ensures that the load of every facility is at most T. The second constraint ensures that the size of the cover is at most K. Third and fourth constraints ensure that every client is served fully and is assigned only to open facilities. The last constraint removes any facility client pair that have distance greater than T, since in any star cover of load at most T, this facility and client will never get matched. This linear program is considered standard for minimum load K star cover problem and was previously used to derive several approximation algorithms for particular cases of the problem. We will use it for the general case. Given facility I, let Lix denote the fraction load of I with respect to assignment X. We call a solution xy to SCLP alpha beta approximate if the load constraint is violated by quarter fraction of alpha, factor of alpha, and we open at most beta k facilities, and all the other constraints are perfectly satisfied. On a very high level, our algorithm for MLKSC works as follows. Using binary search, we find the value T star of load that is close to the optimum by solving SCLP multiple times and checking its feasibility. Quite a standard procedure. Having obtained such value T star, we solve the star cover LP with parameters T star and K, and obtain a feasible solution X star Y star. Then we round this solution to get the desired integral by criteria approximation. Using the same LP, but optimizing over the number of open facilities, we get a bicriterial approximation for the minimum size star cover problem. The rounding algorithm for this problem is quite different, but utilize the same ideas and tools. So we'll focus on describing the rounding algorithm for minimum load K star cover problem instead. The first observation is that it's sufficient to find alpha beta approximate solution xy with only y integral, that is, determine the set of open facilities and make them fractionally serve all the clients. Then we can use minimum maximum rounding by Lenstra, Schmois, and Tardash to get integral assignments sacrificing a factor of 2 in load approximation. So our aim is to decide which facilities to open fully and which to close, and how to redistribute the demand of all clients between the opened facilities, so that the resulting solution is feasible by criteria approximation of our desire. This is precisely what we are going to get. Let me explain in more detail how the redistribution process works, which I call rerouting. Given a solution xy and pair of facilities I and h, when I close I and reroute all demanded circ to h, I basically create a new assignment xcirc, which removes the demand associated with I and adds it to the current demand of h, leaving all the other variables unchanged. We can upper bound the change of the load of h using triangle inequality. It will be at most the sum of previous loads of h and I plus the distance between the facilities times the number of rerouted clients. There are some difficulties arising when we try to route facilities. It is clear that if the old load of I and h is bounded, then the new load of h will be bounded too, if and only if the IH distance times the number of routed clients is also bounded. However, what if we cannot route I to any other facility, since this value is substantially larger than bound T? A natural idea is to try to open I itself and make it serve all of its clients fully. However, what if the integral load of I that we obtain by doing so is also large? We can avoid having integral load of facilities being large by using some sophisticated tricks. Suppose that for every facility client pair ij, the value of xij is either 0 or at least by I times some constant y, times constant gamma. In this case, if the fractional load of I was bounded, opening integrally and making it serve its clients fully will blow up its current load at most by a factor 1 over gamma, which is constant. It turns out that we can guarantee such property for the solution xy of the LP by slightly relaxing the constraints, precisely increasing the fractional load by a small factor and sacrificing at most gamma fraction of each client's demand. We call this transformation from xy to x prime y prime with desired properties preprocessing, and it can be done in polynomial time using the modification of minimum makespan rounding algorithm by Lenstra et al. Clearly, after the transformation, any facility can be opened integrally, and its load will not exceed T by too much. Our algorithm starts by applying the pre-processing step. Let dj for client j denote its average facility client distance. Using well-known filtering technique by Lin and Victor and applying pre-processing step, we get a solution x prime y prime with the following properties. Basically, we get lower bounds on all variables xi, j, which allows us integral opening, and also we get an upper bound on each facility client distance in terms of the average distance. And for that, we sacrifice a small portion of each client demand, as well as possibly increasing total opening by epsilon k. Note that losing a fraction of client's demand is not a problem. Having obtained integral opening, we can simply scale all assignment variables and regain the lost demand. This will not increase our load significantly, since everything is constant. Initially, the load of all our facilities is bounded. We would like to identify facilities I that cannot be rerouted precisely their distance times the number of clients is too large, as we mentioned before. We call a facility heavy if the sum of average distances of the clients it serves is greater than T over epsilon. We use this definition for the following reasons. If I is non-heavy, then T over epsilon is an upper bound on the number of served clients times their minimum average distance. We will try to get rid of all heavy facilities by integrally opening them, and then find a way to reroute non-heavy facilities, so that the facility distance is bounded by the minimum average distance of a routed facility. By doing so, we may hope to guarantee that the additional load after routing will not become too large, as we will have an upper bound of T over epsilon. First, we open all heavy facilities. It is done very straightforwardly. We scan all facilities I, and if I is heavy, we simply open it and make it serve its clients fully. During this process, some facilities that were heavy may become non-heavy, because part of their clients may have been changed and delegated to another heavy facility in its opening. And this is perfectly fine. One can show that totally we will open at most epsilon k additional facilities, and owing to pre-processing step, the resulting load of each opened facility will be at most big O of T over epsilon. From now on, we will assume that all facilities are non-heavy for convenience. Our next goal is to group up clients for rerouting. We are going to partition set F into disjoint clusters so that the distance between every two facilities within the same cluster is bounded in terms of minimum average distance of the clients they serve. The clustering is done in two steps. First, we decide which clients will be cluster centers, and then we assign every facility to corresponding cluster center. Cluster centers are chosen as follows. We scan clients in ascending order of their average distance and add client and make client a center if it is sufficiently far from all previous cluster centers. We form clusters as follows. If facility I serves some cluster center S, we add it to its cluster. Note that each facility can be served by at most one cluster center simultaneously. If I is not served by any cluster center, then consider J, the client with minimum average distance among the clients I serves. Observe that J is not a cluster center. We add I to cluster center centered at S that prevented J from becoming one. After this process, every facility will be assigned to its cluster. It turns out that it is possible to get a desired bound on facility distance after this clustering procedure. Let C of I be the center of I's cluster. We show that if J is a client with minimum average distance served by I, then the distance between I and its cluster center is at most 3 over epsilon times dj. Applying triangle inequality immediately gives us the desired upper bound on the distance between the facilities within the same cluster. Finally, we are going to open some facilities in every cluster, close the others, and route closed facilities into opened ones in the same cluster. Note that by construction, each cluster includes all facilities that serve its center. As a result, the total opening in every cluster must be at least 1 over 1 plus epsilon. This fact will allow us to bound the total number of open facilities. The final steps of the algorithm are as follows. In every cluster, we sort its facilities in ascending order of minimum average distance and open this many first facilities. After that, the demand of every closed facility in the cluster is redistributed at equal fraction between all open facilities within the same cluster. It is easy to see that the total opening after this procedure will be at most 1 plus 3 epsilon times k. What about the upper bound on the resulting load of every open facility? Let Ks denote the number of facilities we opened in cluster centered at S. Suppose we closed I and routed it into opened H. We can bound the additional opening H gets the same way as before. Using the known bound on initial facility load, as well as LP constraint bounds, we further simplify the expressions, substituting previously obtained bounds on facility distance. Finally, since all facilities are non-heavy, we can eliminate the number average distance term from our bounds, getting a nice expression. Applying this bound to all facilities I that we routed into H, we can get an upper bound on the total additional load H gets after rerouting. As a result, we obtain a solution x hat y hat with integral y and fractional x, which is the desired bicriterial approximation. We apply the earlier mentioned techniques to obtain an integral assignment, which finishes the algorithm. We also obtained some lower bounds for the linear programming approach to minimum load K-star cover problem. More specifically, we can construct a family of instances such that any integral cover of size at most 1 plus epsilon k has load at least 1 over epsilon times the optimal LP value. This basically shows that our algorithm is not very far from the best possible approximation we can get using the same LP relaxation. Similar issues arise with the minimum size star cover problem. We construct a family of instances such that there is a fractional cover of load at most t, but any integral cover has load at least 2 minus epsilon times t, even if we allow all facilities to be open. This suggests that the approximation factor for maximum load we obtain in MSSC algorithm is close to the best possible if we try to use the same LP. These problems are quite poorly studied, so there are many open questions that still remain unsolved. For example, it would be interesting to see some general hardness approximation results for any of the problems. Our bounds show the limitations only of the LP-based approach. Moreover, they are not tight. Also, one would wonder if we can obtain better approximation for these problems, possibly based on different LP relaxations, or not using linear programming at all. That's all. Thank you for your attention.